At the onset of this section, you had just done the applet on is yawning contagious. So let's move on to review some key concepts about proportions first. Recall in Chapter 6 that we wanted to talk about what happens when you combine two random variables. How does their mean change and how does their standard deviation or variance change? When you take the difference of two random variables, remember you just subtract the two mean values. To find the new standard deviation of the two variables once they're combined, first you must find the variance of those variables. The difference in their variance is adding those together. And then to find the standard deviation, we would come on in and take the square root of that. Then we moved on to Chapter 7, which is the sampling distributions. Recall that the mu of p hat, or the mean of a sampling distribution, which is many, many samples of p hat, is p, or the population parameter. The standard deviation of p hat is the square root of p times 1 minus p over n. Chapter 8 and 9 then introduce confidence intervals and hypothesis tests. Recall for Chapter 8 we use p hat in our confidence intervals, and for Chapter 9 we use p naught in our tests. That is, the formula for the confidence interval is stated here. It's very similar as looking at the sampling distribution information, but in this case we use our p hats. For our testing then, remember our hypothesis actually used what we thought p naught would be, and we could either choose a one or two-sided test for our alternative. The test statistic then for that uses the actual sample proportion, or our p hat, minus our p naught over the standard deviation using the p naughts. So we've seen a lot of connections between Chapters 7, 8, and 9 as it relates to proportions and how they're used for computing the sampling distributions, confidence intervals, and doing tests. Now it's important for us to have a grasp of this information because in Chapter 10 what we're going to do is focus on doing confidence intervals and tests of finding the difference of two proportions of two different samples. So we're going to have to reference our information that we know from Chapter 6 again. So in 10.1a and b, we're going to describe the characteristics of a sampling distribution of p hat 1 minus p hat 2. And then we're going to calculate some probabilities using the difference of that distribution. So when we're now asked to look at the sampling distribution for the difference between two independent variables that are proportions, what we're going to look at is we want to see the sampling distribution of p hat 1 minus p hat 2. What's the difference? Well, we are going to have to check for some normalcy. They are going to be independent, and of course they'll be random. How do you compute the new mean? The mean is just like we did before for the differences. It's going to be p1 minus p2. How do you find the standard deviation? Well, the standard deviation is going to be the same formula we've used for the sampling distributions. We have to find the variance of sample 1, add to it the variance of sample 2, combine those because when you bring two variables together, even though you find the difference, you do increase the variability. To find the standard deviation, take the square root of that combined variance, and this would be considered the sigma of p hat 1 minus p hat 2. Notice the notation. What we're finding is the difference of two sampling distributions. So back in Chapter 7, for the mu of just p hat, we find the difference of mu of the two p hats. We are using just the population parameters, not the p hats in their calcs. For the standard deviation, again, it is the difference in the two sampling distributions. So again, we use p1 and p2, not the p hat values. Because in Chapter 7, for sampling distributions, you use your population parameters. In 10.1c, we will also talk about the conditions that need to be tested when we find the sampling distribution of p hat 1 minus p hat 2. The conditions are just what you would expect, but it's pretty much 2 times of what you have to do. The first thing is you have to show that the SRS from population 1 and from population 2 both exist. It's basically doubling up your work. When we just looked at one population before, we just did, is there an SRS from one population? But since there's 2 populations at hand, you just have to do it one more time. How do you check the 10% condition? For independence, same thing, nothing different. For this case, the 10% condition has always been, is the population greater than or equal to 10 times the sample size? Well, you have to do it for sample 1, and you have to show it for sample 2, and it must meet for both of those. For approximately normal, for proportions, Again, same thing, nothing has changed, but we do it twice. We're going to identify the n times p and n times 1 minus p for the first sample, and then we're going to do it for the second sample. All four of these must be greater than or equal to 10, so make sure you show all four calculations. Let's look at this example that brings together all three of those learning objectives into one problem. Who does more homework example? Suppose that two counselors at school 1, Michelle and Julie, independently take a random sample of 100 students from their school and record the proportion of students that did their homework last night. When they're finished, they find the difference in their proportions. So they're choosing Michelle's minus Julie's. And the difference was for their sample 0.08. They were surprised to get a big difference, considering they were sampling from the same population. So describe the shape, center, and spread of the sampling distribution. So basically, question A, we need to compute what the new sample mean and standard deviation are for these instances. Remember, in order for us to create the new sample standard deviation, we must show that the independence rule is met. But in this case, we're actually okay because it said they were already independently taken. So I do not need to check for that 10% condition. Let's go ahead then, assume the 10% condition is taken care of. By the way, it is a random sample. Let's wrap up with confirming the normalcy. So for the normalcy condition, we're going to check n times p and n times 1 minus p for both Michelle's situation and for Julie's. All four of these must be greater than or equal to 10. Since they are, we know that the sampling distribution of Michelle minus Julie's proportions is approximately normal. Let's compute the mean. Now, in this case, I do want to tell you this upfront information. The population of students is 2,000 students, and we're assuming the true proportion is 70% of their students did their homework last night. So we're going to say the proportion of Michelle minus proportion of Julie. Well, it would be the same because they're sampling from the same school, so we think the difference is 0. And that's what they're saying. They were surprised it came in at 0.08 because they're sampling from the same students. Why wouldn't the difference be 0? Now, based on this, let's go ahead and compute the standard deviation. So again, we're using the population proportion, so it's going to be 0.7 and 0.3 over 100 for each of the two counselors. Add it, then we'll take the square root of that in order to get us our standard deviation that we need. So in terms of describing the shape, center, and spread, our shape is approximately normal, our center is at 0, and our spread is 0.065. In part B, let's find the probability of getting two proportions that are at least 0.08. Now, from here, remember we found the new mean and standard deviation. So technically, I could do a quick sketch of that. The sketch of this is going to be in this normal curve here, where the mean difference is right in the middle. Every standard deviation is 0.065. So this is one standard deviation, 2, and 3 from the mean. What's the probability that two proportions are at least 0.08 apart? So you're going to notice they went on here on the curve, 0.08, and got the right-hand tail. But you have to be careful in here because you could also be in the other direction. So in this direction, it could be this tail. So really, the probability on here is tricky. It's both of the two tails together. So to find the probability, what we really want to calculate is the probability that the difference is less than negative 0.08 or greater than positive 0.08. What we could do is we could do normal CDF for this tail and double it, or we could just find it for both. So in this case, we have our sampling distribution and our decided shaded area to the right. If I use technology, I'm just going to do normal CDF on the left-hand tail from negative 100 to negative 0.08 with our new mean and standard deviation. Then we're going to add to it the right-hand side, which is really just double of that. That'll give us a final probability of a 21.84%. The ultimate question, should the counselors have been surprised to get this difference? Well, since the probability isn't very small, we shouldn't be surprised to get a difference of sampling proportions of 0.08 or bigger, just by chance, even when sampling from the same population. Again, if the probability is over 21% chance that it happens, they saw an 8% difference in there, which seems reasonable since the probability was fairly high to happen in the first place.